So this is a rerun for the first PMRF TA session for the course NPTEL course, Approximate Methods in Quantum Chemistry, which was held last week. Unfortunately, because of some technical difficulty, the recording was not done properly. So so this is a rerun where I will be solving all those problems that were discussed in that session, and so it will be useful for the learners who joined the session, and as well for the people who will be watching these videos, these sessions on YouTube. Okay, a quick intro of mine. I am a PhD student, Prime Minister Research Fellow, PMRF, in the Solid State and Structure Chemistry Unit, SSU of Indian Institute of Science, IISc Bengal, and I am an NPTEL-PMRF TA for this course, Approximate Methods in Quantum Chemistry, and there are going to be 8 total 2-hour interactive sessions, one of which was held last week, and this is a rerun for that. Okay. So first problem that we solved was for that we were given a matrix A, which is given as 0, J0. Just 1 minute. Let me just, okay, yeah. Sorry for that. Okay. So yeah, so what we have here is we have a matrix A given as 0, J0, a very simple matrix. So in the A part, we have to find the eigenvalues and eigenvectors for this matrix A. So as you might know, to do this, we need to write this equation A minus lambda I times x vector equals to 0, where this I is our identity matrix, which is given as 1, 1, 0, 0. This is our identity matrix. Lambdas will give us our eigenvalues, and the x vector is basically gives us our eigenvector. Okay, so here let's see what our A minus lambda I is. Here I will check our A minus lambda I. That will come as, A is 0, J0, it will come as minus lambda J minus lambda. This will be our A minus lambda I matrix. And now to solve this equation, this above equation, what we need to get the determinant of A minus lambda I, this matrix, to be equals to 0 to get a non-trivial solution. And if we do that, we have minus lambda J minus lambda, determinant equals to 0. This gives lambda square equals to J. Okay, you can see lambda square minus, okay, let me just write properly. It's lambda square minus J square equals to 0. So lambda will come as plus minus J. So these are our eigenvalues. Okay, and so for eigenvalue, now we need to find our eigenvector. For eigenvalue lambda equals to J, we can write our equation again. Our equation was A minus lambda I times the x vector equals to 0, and we now want to find our x vector, our eigenvector. Now for lambda equals to J, our A minus lambda I, as you might guess, it will be minus J minus J times x vector, which will be x1, x2. You can take x1, x2 equals to 0. From here we will have two equations, both will give the same result. So one equation that we get is minus x1j plus x2j, that will be equals to 0, and from here we get x1 is equals to x2. So for lambda equals to J eigenvalue, our eigenvector x vector we can write as taking x1 equals to 1, 1, 1. So this is our eigenvalue and our eigenvector. Now the second part, not the second part, but like this, our second eigenvalue, which was lambda equals to minus J. For lambda equals to minus J now, let's make it in that form only. For lambda equals to minus J, our equation again, it is A minus lambda I times the x vector equals to 0. So again we have for lambda equals to minus J, our equation will be, our matrix will be J times x1, x2, that has to be equals to 0. From here you can see, oh sorry for that, let me just remove it for now. Okay, this will come back. Just remove this one. Sorry about that. Okay, I guess, okay, so this is already some solutions are there. We will solve everything this. Just 1 minute. sorry about it. Okay, so we are here. Okay, so we have this. We will write this from here. We get, as you can see, jx1 jx2 equals to 0. This will give us x1 equals to minus of x2. Correct. So for that, from here we get for our eigenvector lambda equals to minus j. Our for eigenvalue lambda equals to minus j. Our eigenvector taking x1 equals to 1, we can write as 1 minus 1. Alright. So this is our A part, this was our A part to find the eigenvalues and eigenvectors for this matrix A. Now the second part is the diagonalization of the given matrix A. So what diagonalization does is, basically for diagonalization means that we go from A somehow to a diagonal matrix D, which, and the diagonal matrix is such that like we have a 2 cross 2 A matrix, so we will have a 2 cross 2 diagonal matrix. And a diagonal matrix is the one which has only the diagonal elements as non-zero and the non-diagonal elements as 0. And what will happen is that when we diagonalize our matrix A to, we transform our matrix A to a matrix D, which is called the diagonalization of matrix A, where we get a diagonal matrix like this, and the diagonal elements will be our eigenvalues. Okay. To do that, we will need a unitary matrix. A unitary matrix or a unitary operator also, a unitary operator is basically defined as this: U adjoint equals to inverse of that U minus, and in matrix formalism of quantum mechanics, taking an adjoint is basically taking a transpose and a complex conjugate of all the elements. Okay. So here we will be there, and here at the end we will also see what is the significance of this U matrix. The importance of solving this problem is that this diagonalization method is basically used in the quantum chemistry software packages to find the eigenvalues and eigenvectors. So the program does, it finds a unitary matrix U to diagonalize your say Hamiltonian matrix, and by using this U matrix to diagonalize that Hamiltonian matrix, we finally get our eigenvalues and the eigenvectors. Okay, so let's just do that. Okay, so we need to find out D, and we will get our diagonal matrix by U adjoint AU by doing this. And let me just write what our U is. Our U here is 1 by root 2, 1 by root 2, minus 1 by root 2, and 1 by root 2. Okay, so let me just check. So we have our U, which is 1 by root 2. Sorry about that. Okay, we have 1 by root 2 minus 1 by root 2, 1 by root 2, and 1 by root 2. Alright, so this is our unitary matrix, U matrix. Okay, 1 by root 2 minus 1 by root 2. Sorry, I guess I got the wrong minus from. Okay, let me just check here again. Okay, so this is 1 by root 2, 1 by root 2, minus 1 by root 2, and 1 by root 2. Yeah, this is our U matrix. 1 by root 2, 1 by 2, minus 1 by 2. Okay, now we will take the adjoint of it, which is just taking the transpose in this case. All the elements are already here. We will have 1 by root 2, 1 by root 2, minus 1 by root 2, 1 by root 2, times our A matrix, which is 0, J, J, 0, times U, which is here you can see. Here you can see, sorry. Okay, 1 by root 2, 1 by root 2, minus 1 by root 2, and 1 by root 2. Right. So here, if we do this calculation, so matrixation, first row into first column, we get minus j by root 2, and this will be j by root 2, this will be j by root 2, and this will be also j by root 2, times 1 by root 2, 1 by root 2, minus 1 by root 2, and 1 by root 2. Right. So again multiplying first row with first column, minus j by 2, minus j by 2, we get minus j first row into the second column, which is minus j by 2 plus j by 2 0. Second row into the first column, j by 2 minus j by 2 0, and second row with the second column, j by 2 plus j by 2 j. So this is our diagonal matrix T. And here, from here, this diagonal matrix T, we can say that our lambda, our eigenvalues are plus minus j, what we obtained earlier. And also, if you remember, okay, and our U matrix, if you see our U matrix, let me just write it again. Our U matrix that we have used, unitary matrix, to diagonalize here our A matrix, it is this. So from here, as you can see, as you remember, for lambda equals to minus j, our eigenvector was 1 minus 1. And here also, from here, we can see that for lambda equals to minus j, which is the first element of the diagonal matrix that we obtained, our eigenvector will be equals to the first column of the unitary matrix. So our x vector will be equals to 1 by root 2 times 1 minus 1. So this is what we obtained. And also for the second element, it will be the second column. So lambda equals to j, but we will have our eigenvector equals to 1 by root 2 times 1 1. And this 1 by root 2 doesn't matter, it is just a scalar. So mainly what we found the eigenvectors as 1 minus 1 and 1 1. And this 1 by 2 is just a scalar. You can multiply a scalar to an eigenvector, that will also be an eigenvector. So this was our problem 1 of the session. Okay, now we will go to problem 2 that was discussed in the previous session. So in this problem, we basically proved this for identities about our operators and their adjoint and their commutations. Okay, so mainly we are going to use this relation. As you can see here, this is an important relation. Like if you know the cat, I can write my cat psi prime as a cap times cat psi, and then the bra will be written like this. The bra of psi prime will be equal to bra of psi times the adjoint of that operator. Alright, so let's solve each of these identities. So first identity that we're solving is this one, psi a adjoint phi equals to phi a cap psi. Okay, so to do that, what we are going to use is so we have to solve this. Basically we have to solve psi a cap adjoint phi equals to, we have to solve that this has to be, is it equals to this we need to prove. Okay, to prove that, we are going to use this conjugation. You can say this is a form of conjugation relation, which is psi prime phi should be equals to phi psi prime star. Alright, and here our psi prime, as I have written above, it is basically, it is our a cap acting on cat psi. Alright, psi prime is basically equals to this. So from here itself, just using this relation, just using this one, what we can say that, okay, so we know that this psi prime phi we could be written as phi psi prime star. So using that thing, that relation, and we know, like if our cat psi prime is this, then our bra psi prime will be just equals to bra of psi a cap adjoint. So replacing those things, we can write this as psi a cap adjoint phi is equals to, we will have phi, and we just write psi, which is whatever our psi prime is, which is a cap psi star. And this is the identity that we had to prove. So this was a simple proof. Psi a cap adjoint phi equals to phi a cap psi complex conjugate. Alright, this star is complex conjugate. Okay, I hope you understand it. Okay, now the second identity that we have to prove is, if we have taken adjoint of an operator, then that gives us the same operator. Now to do that, we are going to actually use this identity that we have proved in step A. Okay, so to do that, what we will do is, we have psi a cap adjoint. Okay, so for this, instead of a cap adjoint, let me just change it a little bit. Instead of using a cap adjoint, let's say I'm saying that, okay, my b cap is equals to a cap adjoint. Okay, this is my operator b cap. I'm writing it as a cap adjoint. Now using this previous identity that we proved, psi b cap adjoint phi Now this, so let us just write it in a form that, that shows what we are proving. So okay, so we have psi a cap adjoint equals to phi. This I will write it as psi some b cap operator adjoint phi. Then from the previous identity I can write it as phi b cap psi star complex conjugate, and then I can replace b by a cap adjoint psi star. And again, using the same identity, I can write this thing as psi, taking this is the okay. So this. So okay, yeah. Using the same identity again, what I can do is I can take this let us write it like this. So you are taking the complex conjugate of just not write it like this. Okay. So basically, I can write this thing as again using the same thing. I can write it as psi a cap phi star, taking the complex conjugate. Okay. We can again apply the same thing. Basically, it is just writing the previous identity, and then we know that taking the complex conjugate of again a complex conjugate will give you that number. It's again. So we will get this psi a cap phi from here, and this, and from here what we have proved, we have proved our identity. So just by comparing these two, you can say that a cap adjoint will give you a cap. Alright, so we have proved our second identity. Now let's go into our third identity. Our third identity is a times a cap adjoint. Okay, third identity is a times a cap in the whole adjoint. Okay, 1 minute. Right. Sorry. So that will be equals to a star a cap adjoint. Alright. So this is what we have to prove. We will again go with our same thing. We get psi a times a cap adjoint, okay, times phi. Let's say this is again this. Okay, now again going with the same thing. What we can write it here is that we can write it as phi, and this will go away. We will have a cap adjoint will go away, psi, and I can write the complex conjugate using the same identity a. Now from here I can take out a, which is a scalar. It will become as a star phi a cap psi. We will have star. Again, using the same identity, we can write this as psi a cap adjoint phi, and we can bring back the scalar. We will have psi a star a dagger phi, and now just you can compare these two. By comparing these two, what we get is a cap whole adjoint is equals to a star a cap adjoint. So this is our third identity. Let's go to our fourth identity, which is a cap plus b cap adjoint. So how we have to open this a cap plus b cap whole adjoint. This should open as a cap plus b cap adjoint. This is what we have to do. Now next identity. To do that, again we are going to use the similar technique that we have used till now. Okay, so this could be written as phi a cap plus b cap and psi star. Okay, now since okay, sorry about that. Let me just go again. Okay, now you can see the screen. Okay, yeah. So okay, now we can write this as phi a cap psi star plus phi b cap psi star. Alright, and using our previous identity, I can write this as psi a cap adjoint phi plus psi b cap adjoint phi. Alright, so okay, so we have this, and then again we can write this as a cap adjoint plus b cap adjoint dagger, b cap dagger plus b dagger phi. again by comparing these two, what we get is a cap plus b cap or adjoint is equals to a cap dagger plus b cap dagger. So we have proved this identity as well. Okay, now let's us prove our next identity, eighth one. So in E, what we have is basically a cap, b cap, whole dagger. This should open as b cap dagger, a dagger. Okay, you can see. All right. So here, what we are going to use is we are going to use something different. So what we can do is, okay, we have like so let's say we have psi prime, that is okay, we have psi prime, which is which we can write as let's say we can write psi prime is given by a cap p cap times a vector psi, and let's say we are saying that this is some cat I. So what we have a cap I. So now we know that if we have to write a psi, we have to write the bra psi prime, bra psi prime, that will be equals to bra of chi times e cap adjoint, and similarly we know that bra of chi will be is equals to bra of psi b cap dagger. Just replacing it there, what we have is we have this psi prime, and also like we know how the bra of psi prime will also be written. We know that it will be written as a bra of psi a cap b cap or adjoint, and then bra of chi will open as bra of psi b cap adjoint a cap adjoint. So by comparing these two, we can say that a cap b cap or adjoint or dagger is equals to b cap dagger a cap dagger. Alright. Now we go to our next identity, our sixth identity, f, and f is basically it's a commutation relation. This is the same thing, just we are multiplying. We have four operators. Okay. Yeah, so we have a cap, b cap, c cap, d cap, or dagger. This will open as b cap, c cap, b cap dagger, and b cap dagger. So you can see that once we have solved for two operators, we can actually use the same technique for many other operators as well, and it will be basically just reverse. So you can just remember that if you have bunch of operators being multiplied and you take the adjoint of the whole multiplication, then it will open as the dagger or the adjoint of all the operators, just in the reverse order. Okay, and let's just prove it. Just quickly prove this one, which this I can write as a cap b cap because it's J1, and this c cap b cap, let's say we call it some operator J2. So what we have again is J1 cap, J2 cap, whole dagger, and this we have proved that this should open as J2 dagger and J1 dagger. And now to open J2 dagger, J2 is nothing but c cap, d cap, whole dagger, and J1 dagger will be a cap, b cap, adjoint or dagger. Now this will open as d dagger, c dagger, and this will open as b dagger, a dagger, and thus we have proved our relation which we wanted to prove. Okay. Going to our next identity. In the next identity, what we have to prove here, this is for a commutation relation. So let's say we have a cap, b cap, c cap. So we need to find how it will be, how to open this commutation relation, and this is what the G with what we are proving right now. Okay. So this is the G1 that we are proving. Okay. Alright. So to prove this, what we will do is, okay, now we will take this as some J operator, and we have a cap comma j cap. Now this we know how to open. We know it is a cap j cap minus j cap a cap. So, and again we will replace this will be written as a cap b cap c cap minus j cap will be written as again b cap c cap a cap. Now we need to make some more commutations from here. To do that, we will add b cap A cap C cap minus B cap A cap C cap. Right, and from here we can take these two commons. We can take A B C and we can take minus B A C, and we can take B A C and not together we can take this B C A. Alright, so from here, now here we can take common the C. We cannot change the order of the operators, that we need to remember. And here I can take the B operator out. It will be A cap C cap minus C cap A cap. And from here we will get A cap comma B cap times C cap plus B cap times A cap comma C cap. So this is what we have proved. This is what we have to prove. Okay, so this commutation of A with B with the multiplication BC operator will be AB times C plus B times operator of commutation of operators A and C. Alright, and this is a really important identity. This G identity is very important. So it's an important one. G identity is important, and as you will see in how it will be useful. So you can remember this thing as like the sequence of this multiplication B and C. So B is on the leftmost side. So basically this commutation will open into two more commutations because we have two operators in the multiplication. So we will have one commutation of A and B, and we will have one commutation of A and C, and the order of B and C will not change. So if B is on the right side, left side of C, so it will open as B times the commutation of A and C. It will be on the right side of C. Similarly, if C, my mistake. Okay, sorry. So basically, if B is on the left side of C, so it will remain on the left side of C. So one commutation you will have is of A and C, and you will multiply on the left side with B. Similarly, C is on the right side of B, so you will make a commutation of A and B, and then you will write C on the right side. So B will remain on the left side of C, and C will remain on the right side of B. So like this you can remember this identity. Let's go our H identity, which has two on both the side. There are this multiplication of operators. Okay, all right. So our H identity, and we will use our what we have learned in our J identity to solve this problem. So we will have AB times J. Now instead of doing the same thing, we will use the identity that we have proved in G. So this ABJ will open as this will open as, so we will have two commutation. We will have commutation of we will have commutation of A with, we will have commutation of A with J, and we will have commutation of B with J, and since A is B was on the right of A, we will have B here, and similarly since A is on the left, we will have A here. Alright, so this is how this will open, and then we will write the same thing A, and we open J. So this is what we have taken J. Okay, CD, I can write CD times B plus A times B CD operators, and here also what we can write it as how this will open. This will also open the same way. C is on the left side and the remaining A and D commutation, plus D is on the right side and A and C commute. Okay, so this is how this commutation will open, times the B operator, plus we will have our A operator times, we will have, sorry about this, okay, we will have our C operator times commutation of B and D plus C is on the left side, and now the D is on the right side. D is on the right side, and we have commutation of remaining B and C. So what we will have from all this, we will have C, A and D commutation times B plus AC commutation times DB plus AC times commutation of PD plus A times commutation of BC times D. Okay, so this will be our final result. Okay, so you can check it. This is correct. Okay, and you can open it and check, but this is like a quick way to do this kind of problems. Okay, now we will go to identity I, and our ith identity is again one of the commutation. So we have to show identity. Ith identity is just about if we have A plus B and commuting with operator C. So how that will open. So we are going to see. Okay, so we have this commutation. We have A plus B commutation with C. So again you can take this A, B as just an operator J, comma C. Now we know how this opens. This will be C cap, G cap, C cap, G cap. Now we will write J as A cap plus B cap times C cap minus C cap times A cap plus B cap. This will give us A cap C cap plus B cap C cap minus C cap A cap minus C cap B cap. From here, what you can see that this is basically the we can take this together. We can take A cap C cap minus C cap A cap plus B cap C cap minus C cap B cap together. This is the commutation of A and C plus commutation of B with C. So that is what, okay, so that is the identity that we have to prove. Okay, so this is the identity, and now we will do one more identity, which is basically the use of this identity I, which we just use identity I. Now we will have A plus B and C plus D, and we can just use this identity to solve this kind of problem. So we have A plus B, comma, we have commutation like this. Let's take this is our J operator. We can write it as A plus B and operator J. This we know will open as AJ plus BJ, and we will replace J with C plus D, B with C plus D. So this will give us AC plus AD plus this will give us BC plus BD. So this is our last identity that we have to prove. So this is also we have to. Alright. Okay, so now we will go to our next problem, which is also okay. So in this problem, what we have three operators. Okay, let me just I will have to draw let me just draw it. So basically what we have is we have three operators A, B and C, and we can as these operators are basically corresponds to some observables in the real world. So what we are going to do, we are going to do a thought experiment. Let's say we have these three operators, and these have this corresponding eigenvalues and eigenvectors given by Bi's and Ci's. Okay, and we will assume that A and B commute with each other, so they are compatible observables. And while A and C doesn't commute with each other, and B and C doesn't commute with each other, so they are non-compatible with each other. And then now we have to find the results for an experiment that I am going to draw now, a thought experiment. And what we are going to let's say we have our system in state psi, and it's given that for this experiment that psi is not an eigenvector of any of these observables, and we are applying we are using the operator A, then we will get some we will get some cat, and then we will applying operator B is basically we are trying to measure like we are trying to measure the momentum of the like if it is a momentum operator, we are trying to measure the momentum of the state of our system, or if it is a kinetic energy operator, we are trying to measure the kinetic energy. So sorry, okay, then okay, here we will get some eigenvalue. So in this box we will keep our whatever values we are getting. Okay, here whatever the values that we are observing, and in this box in big box we will have our state of the system. Then our operating B, we will get some value in the experiment, and then our system will be in some state. Then we will again apply operator C. Again our system will give us some value, our experiment will give us some value, and our system will go into some state. Okay, now we will again apply operator A, and our system will go, we will get some value from our experiment, and our system will go to some another state. And let's say we again operate B, and we will again operate okay, sorry, I guess there is some connection issue suddenly. Okay, so there was some okay, sorry about that, there was some problem. Okay, so this is our basically experiment. Okay, so now let's see what happens. So we have our state in our system in state psi, and when we will apply this operator A, so since as you might know, this state psi, since our A operator is these are observable, so they are Hermitian operators, so their eigenvalues will make a complete basis set. So I can write our psi as summation our JCJ AJs. Okay, so when I operate my operator E on it, I will get one of these, so our wave function psi will collapse to one of these eigenvectors of operator E. So let's say it collapses to some E1, and we will get value E1. So now our system will be in some state E1. Okay. Now we will apply operator B. Now since operator B commutes with, let me just 1 minute, just check if this is working. Okay, sorry. Okay, now okay, as we know that okay, this operator A1 okay, yeah, sorry. Okay, so so as you can see, when we will apply this operator B on this eigenvector A, since A and B commute with each other, so this will also act as an eigenvector of B as well, and give us some eigenvalue of B only. So let's say this will be not only an A1 vector, this will be an eigenvector of B as well, and will give us some eigenvalue, let's say B1. So in our experiment we will get the value B1, and now our system is in this state A1 B1 still. Okay, so this B vector basically doesn't change the state of our system. When we operate B on our wave function, it doesn't change the state of the system. It just gives the value corresponding to that eigenvector, which is, let's say, B1. Now we will operate our operator C on this wave function A1 B1. Now since C doesn't commute with A1 and B1, For C, it is similar to what psi was for our operator A. So A1, B1 could be written as summation over J, let's say dj kets of CJs. Okay, so what will happen is that our eigenvector A1, B1 now will collapse to one of the eigenvectors of operator C. Let's say we get the eigenvalue C1, and now our system is in ket C1. Now again, this now we will apply operator A. And now since operator A doesn't commute with operator C, I can again write any let's say this C1, this ket C1 would also be again written as let's say some Cj prime times Aj's. So again our system will collapse in one of the eigenvectors, but it may or may not be the A1. So let's say it collapses to some eigenvector A4, giving us the eigenvalue, giving us the eigenvalue A4. Right? Now again B will operate on this eigenvector, and since B commutes with A, it will not change our state of our system and will give us the corresponding value. Let's say it is B4 of that eigenvector, and now the ket of our system it will be one with the eigenvalue A4 and eigenvalue B4. So the B operator doesn't change the eigenvector of A, because A and B have the common set of eigenvectors because they commute. Okay, so this was our problem number 3. Now we go to problem number 4. Okay, so here we have to determine the which of these operators are Hermitians. Now to determine the hermissivity of an operator, so as we know, let me just change it back. Okay, now we know that our operator A, if it is Hermitian, sorry about that. Okay, if it is Hermitian, then E cap will be equals to A cap adjoint. Alright, so from here we have psi, you can write it as psi A cap adjoint phi, and as we have learned, this could be written as phi A cap psi star. Alright, and thus and since this is okay, so now we know that psi A cap adjoint phi could be written as we have learned. It could be, we proved it, that graph phi A cap psi whole star, and then since A is equals to A cap adjoint, I can write it as phi A cap adjoint psi whole star, and again using our identity I can write it as psi A cap phi. So what we have shown here is that for a Hermitian operator, psi what we have, okay, sorry about that. Okay, so basically what we have shown here is that we have phi A cap psi. Okay, let me just write it properly. So what we have shown here for a Hermitian operator, phi A cap psi star will be equals to psi A cap phi. Okay, so to prove that any operator is Hermitian, we have to basically just check if phi A cap psi whole complex conjugate is equals to psi A cap phi. Alright, and let's just do some examples for that. Okay, so our first operator is our position operator x cap, which is equals to x. First we will find this, let's say we will find the simple thing, which is psi x cap phi. Now that, if I write in the integral form, this I can write it as psi star x phi of x. Right, and here also one thing, let me just make sure that psi phi are orthogonal, so psi rho of psi phi will be equals to 0. That we will use in our derivations, because you know that for a Hermitian operator these eigenvectors are orthonormal to each other. So psi phi will be 0, and we will use it in part B and C. So these are orthonormal. Psi and phi are, if our operator is an Hermitian, then we are using this eigenvectors of Hermitians only. So operator only, then psi phi will be equal, will be orthonormal to each other. Okay. Okay. Now, so we have this. Now we need to take a complex conjugate of this whole. So what we can do is, okay, so we have this. Okay, let's say we have this one, and now let's just write the other part, which is phi, and instead of a cap, let's just write x cap, psi O star. Now this will be equals to integration over dx, phi star of x, x, psi of x, O star. That will be equals to dx, phi of x, x, psi star of x. And since we can, here we can move it around, and just moving it around, I can write this as this. And this, you can see, is the relation that we have formed, is similar to what we have formed for this psi a cap x cap phi. So from here, since these two are equal, we can say that x cap is Hermitian. Or our operator x cap is Hermitian. Now let's go to our second problem, which is for this B1. B, I am taking an a cap operator, which is equals to x times del by del x. This is x times del by del x, d by dx. Okay. So I will again write the same psi a cap phi, which will be dx times psi star of x. A cap is x del by del x times phi, which is phi of x. Alright, we'll just keep it like this. Then we will solve phi. Let me just sorry. Okay, now we will write phi a caps plus phi a caps psi star. Okay. Psi star, this will be equals to dx phi star of x, x del by del x, psi of x, whole complex conjugate. Here what we will observe is we will get it is as phi of x, this will be same del by del x, and we get psi star of x. Okay, so from here we have dx phi of x, x times del psi star of x, del x. Now here to what we need is a psi star of x to prove it, so we will do really using integration by parts. So I can write this as phi of x times phi of x, x times psi star of x. Okay, from limits minus infinity to infinity. Alright, minus integration psi star of x, and let me just integration dx times psi star of x, and del by del x of phi of x times x. Alright, now since we know that these wave functions, they are zeros at okay, this they will be zeros at infinity, the wave function as we define. So this term will be 0, this will go to 0. Right, and what we will have, let me just write it here like this, where what we are doing here is integration by parts. By parts, okay, which is basically if you have u dv, it would be written as uv minus integration of v d. Alright, this is the formula that we are using. integration by part integration u dv is equals to uv minus integration v du. Okay, so we integrated our dv psi star del psi star over del x, and that will be 0 because wave functions are 0 at plus minus infinity. And then we have minus integration dx psi star of x and del by del x of the remaining function phi x x. Okay, now this if we have to write again, we will apply integration by parts, and this I can write as psi star of x. Okay, sorry, no, let me just let us open this differentiation. So what we will get is dx times psi star of x times phi of x and minus integration dx psi star of x x times del phi by del x. Alright, now this is basically, this thing is basically psi phi, and since we have taken this, they will be orthonormal. If our operator is Hermitian, then they have to be orthonormal. Eigenvectors have to be orthonormal, so this has to be 0. Now what we are getting is dx psi star of x x del phi by del x. So we are taking psi and phi as orthonormal here. Okay, so just for the proof, we are taking psi and phi as orthonormals. So what we are getting is minus of this, which is basically minus of psi this e cap, psi e cap phi. Now as you can see, so this is here we are getting a negative sign. So this we shouldn't have gotten if e cap was Hermitian. So that proves that e cap equals to x del by del x is not Hermitian. It is not Hermitian because we are getting a minus sign, and since we are getting a minus sign, this is anti-Hermitian. This is called anti-Hermitian. Alright. Now you can solve the C part in the similar manner. C part could be solved in the similar manner. We have b cap is equals to iota x del by del x instead of e cap, and we have to do the seam steps basically. So we can solve this psi b cap phi. Okay. So this we can solve. So I will not explain it. I will just solve it quickly. The explanation is the same what we did earlier. The explanation is same to our previous problem. So I'm just solving this thing. Again, we are using integration by parts. so here you can see what we are getting this time is iota x del by del x times phi of x, which you can write it as psi iota x del by del x is basically your b cap times phi. So we have proved here that it is coming equal to psi b cap phi b cap psi star is coming equal to psi b cap phi. So you can check it, and some here we can say that b cap equals to iota x del by del x is Hermitian. Okay, so this is Hermitian, and okay, so we have proved here, we found that b cap is Hermitian, but a cap was not Hermitian, it was anti-Hermitian. Okay, now moving on to our last problem of the session. So here we are going to prove some identities for the angular momentum operators. Okay, and we will use all these definitions for the angular momentum that you might be knowing. Alright, and also along with this we will be using the x cap p cap is equals to iota h cross. This computational relation also is what we are going to use. Okay, so let's move on to the first one. Let me just 1 minute. Alright, okay, so let us move on. Okay, let us prove the first one. Now in this I will just prove one of the identities, and the rest of the identities could be proven in the similar manner. So I will not prove them. So let's just prove this first identity. Okay, so what we have is Lx comma Ly is equals to iota h cross Lz. Now Lx I can write this as ypz minus zpy. I hope please check how to do this, how to get this Lx, Ly, Lz. They are given by this, and as you know, this is L vector. In classical mechanics, it is R vector plus P vector, and in the similar way in quantum mechanics as well, to get this operator of Lx, Ly, Lz, you just have to do this cross product of R operator, R vector plus P vector, and they will be just they will be similar to what you do in classical mechanics. So and that's how using L vector, R vector plus P vector, you can obtain these relation for Lx, Ly, Lz. Okay, now we have Lx is ypz minus zpy, and Ly is zpx. Zpx minus xpz. Alright, so now using what we have learned in our identities for commutations, we can write it as ypz comma zpx minus ypz comma xpz minus zpy comma zpx and plus zpy comma xpz. Alright, so here, okay, now we have ypz zpx minus ypz commuting with xpz, we have minus zpy commuting with zpx, and at last we have zpy commuting with xpz plus. Now in this case, like we know how to open this computation relation from our identities that we have proved in problem number 2. But now instead of basically doing that, we could do some little smart work, like instead of opening everything, we will use those identity, but let's just do some little mental calculation could also be done here. So what we can see is here that for this identity, let's just observe this one. So for this, using our identity that we have derived for the commutation, we know that this will open and it will give us like 4 commutation. It was 4 terms of commutation. So let's just write them out. Let's just quickly write them out. Okay, we will get commutation between y and z. Then we will get commutation between pz and px. Then we are going to get commutation between PZ and Z as well, and we are going to get computation between PZ and between Y and PX that I have not written. Okay, there will be a commutation relation between Y and PX. I am just opening the first term here. Okay, so we have a commutation YZ, we will have a commutation between PZ PX, we will have a commutation between PZ and Z, and we will have a commutation between Y and PX. And using the identity, we know that like for YZ, PZ will be on the this side because it will be on the right side of this, and PX will also be on the right side of Z. So let me just so this we can open, and also like PX PZ, they commute with each other, so you can write it as PX PZ or PZ PX. That doesn't matter. Okay, the main point is that okay, let me just write this, and we have PZ PX, and the Y will be on this side, and Z will also be on this side, and since both Y and Z commute with each other, we can write either YZ or ZY. That's not a problem. Again, for PZ and Z, Y will be on this side and PX will be on this side, and for YPX, PZ will be on this side and Z will be on this side. Okay, this is based on the identity that we have put. Now here we can see that what we are seeing is that we know that Y and Z commute with each other, so this commutation is going to be 0. Similarly, PZ and PX also commutes with each other, so this commutation will also going to be 0, and YPX also commutes with each other, so this commutation will also be 0. So only non-zero commutation that we are going to observe will be just PZ and Z1. Alright, so and using the identity rule that we have used, we can find this thing. Now we can do the same thing, and I hope you will also be able to now do this mentally. That if you just see that for the second term, you again see that okay, there will be 4 commutation relation. Now Y and X will commute with each other, so their commutation will be 0. Y and PZ will also commute with each other, so their commutation will also be 0. Then we will have a PZ and X commutation, that will also be 0, and then we have a PZ and PZ commutation, that will also be 0. So this term will give us 4 commutation terms, and for all the 4 computation will be 0, so this term will be 0. Similarly, here we will get computation of Z and Z, that will be 0. We will have computation of PY and PX, that will be 0. We have computation of PY and Z, that will also be 0. And PY PX computation is also 0. So basically this is also giving Z with Z 0, Z with PX 0, PY with Z, it also commutes, so computation is 0, and PY PX also commutes, so their computation is 0. So this will also give us 0. And here also we can see that Z and X commute with each other, so that computation term will be 0. Z and PZ, they don't commute with each other, so we get 1 computation term here. While PY and PX, they commute, so that computation term also we don't need to write. And PY and PZ, they also commute with each other, so we don't need to write that commutation relation as well. So only term that we write from this fourth term, only non-zero term will be the one which has the commutation of Z and PZ and we know that and from our identity that we have proved, it will open as we have Z and PZ. Now X will come on this side, alright, and this PY will come on this side based on the identity that we have proved. PY will be on the right of Z and X will be on the left of PZ. Alright, now we know this will give us Y times minus iota H cross times PX. Okay, so this is equals to, this is for X PX, this is equals to Y cap PY cap equals to Z cap PZ cap. Alright. Okay, so since X PX or Z PZ is equals to iota H cross, PZZ, that will be minus iota H cross plus X times iota H cross PY, that will just give us minus iota H cross times or let's just take iota H cross common. What we'll have is X Py minus Y Px, and if you check this is actually the relation for our LZ angular momentum. So here we have proved our first identity, that commutation of Lx cap comma Ly cap is equals to iota h cross Lz. This is our first commutation relation. And similarly, we can prove the other commutation relation as well using the same technique. Only you have to put instead of x and y, you have to put y, and like in the b part, we have to put Ly Lz is equals to, you have to find Ly Lz, and if you write, sorry about that. Okay, Ly Lz, that will be equals to Zp. Sorry about that again. That will be equals to Zpx minus xpz comma xpy minus ypx. Alright, and this we know, this can open as Zpx comma xpy and minus Zpx comma ypx minus xpz comma xpy plus xpz comma ypx. Right? Zpx xpy minus zpx ypx minus xpz xpy plus xpz ypx. Okay. So what we will have here, again we will just by seeing which commutation will survive from the first term, only one commutation will survive, which will be p of px and x, and by the relation it will be, we will have z and py on either side. This term will give no non-zero commutation. This will also not give no non-zero commutation. You can check it. And from here also we will get one commutation non-zero, which is xpx, and we will have pz on this side and y on this side according to the identity that we have proved. So we will have z px x py plus y xpx commutation pz. So from here again this will be equals to minus iota h cross py plus y iota h cross pz, and that will be, where again it is minus zpy plus ypz. Okay, ypz minus zpy, and this you can check, it will be equals to ypz minus zpy equals to iota lx. So this is the identity that we have proved. Okay, it will be equals to, it is coming as iota h cross lx, Ly Lz commutation. Alright, and last C part again I guess you will be able to solve. So I will just write the final terms that you will get, that you might get. If you solve it, you will get these two terms at the end. If you again write what Lz and Lx are, and at the end this will be the surviving terms, and z y py this, and here again you can see this is minus iota h cross pz, and this will be z iota h cross px. Okay, pz, and we have z y py px. Right, we have iota h cross, you can write it as z px minus x pz. Right, z px minus x pz, and that could be written as iota h cross Ly cap. Alright, so these are important identities. Now next commutation relation that we are going to prove is for the L square Lx, and this let us prove. I will just prove it for one part only, and the rest is similar to what we have to do. So this identity just shows that okay, what we have seen from these four identities, that Lx, Ly, Lz they don't commute with each other, while Lx, Ly, Lz they commute with L square. So from this fourth identity, we can say that we can calculate the total angular momentum and the angular momentum and in any one of the direction at a time. Okay, because only that thing commute with each other, but angular momentum in the different directions they don't commute with each other. So we can't find at the same time, we can't find the angular momentum in all the three directions. What we can find. Okay, 1 minute. Sorry about that. Okay, yeah. Let me just do full screen again. Alright, sorry about that. Alright, so from here, that is what is it? That is like you can find the total angular momentum, square, and angular momentum in one of the directions. Okay, so here I'm just gonna prove the for L square and LZ commutation. Now I can write this as Lx square plus Ly square plus Lz square comma Lz commutation. Now as we have learned, this will open as Lz plus this Ly square comma Lz plus square comma Lz. Now I can write these squares as just multiply Lx, so we can open this as Lx times Lx comma Lz plus Lx comma Lz times Lx plus I'm just writing Lx square as Lx times Lx and then just using the identities that we have proved, and this I can write it as Ly comma Lz plus Ly comma Lz Ly plus Lz okay, sorry, Lz and Lz Lz. Okay. Now we know that these two commutations will be 0. This is the same. This commutation of angular momentum with itself will be 0 as a commutation with itself. And sorry about that again. Okay. Now we have proved this identities. We have proved what these commutations are. So this Lx times Lz, Lx Lz commutation will give you minus iota h cross Ly cap. Similarly, we get minus iota h cross Ly cap times Lx cap. Then you get Ly cap times Ly Lz, you get iota h cross Lx cap, and this will be iota h cross Lx cap times you will get Ly cap. Sorry. So from here what we are getting is minus iota h cross Lx cap Ly cap minus iota h cross Ly cap Lx cap plus iota h cross Ly cap Lx cap plus iota h cross Lx cap Ly cap. Alright, and here you can see that all these two terms cancel each other, so we are getting 0. So we have proved that Lk square comma Lz cap, that will be equals to 0. Correct. So you can prove the same thing with Lx and Ly. Now going to the okay. Now going to the other problems. Let's say problem identity number E that we have. So let me just go to E. So for E, what we have is we have L cap, this step up, step down, or ladder of height, whatever they are called. So we have to prove L plus and L minus commutation. What that is going to be? L plus L minus commutation. So it just proved it. So this is Lx plus iota Ly cap comma Lx cap minus iota Ly cap. And what we have learned, okay, now we can just open it as Lx cap plus and minus iota Lx cap comma Ly cap plus iota Ly cap comma Lx cap minus iota and iota square, actually it will be iota square, so it will be minus 1 plus 1 Ly cap comma Ly cap. Now these two commutations, as you might know, these are 0 commutation with each other. This will give a minus iota times now Lx Ly we have found Alex Ly computation is iota H cross LZ. Okay, we have found that Alex Ly is iota H cross LZ, and this will also give minus iota H cross LZ. So this will give us iota square minus, iota square is minus, so we get H 2 times H cross LZ. Alright, so this is the computation of our step down potentials operators. Okay, now next two identities, they are just the computation of this L plus and L minus with the LZ operator. So let me just do F and G. Okay, I'm doing together. Okay, I have written it in, I guess, in the reverse order. This F. So it's F and G, LZ and L plus minus. Okay. LG and L plus minus commutations. So that will give us LZ comma LX cap plus minus Ly cap. So what we can write it as LZ LX cap plus minus iota. Okay, as iota times LZ comma Ly cap. Now LX and this is LX LZ. Okay. Now LZ comma LX, we know LZ LX, we have found out iota H cross alpha, so this will be iota H cross alpha plus minus iota LZ alpha will give us minus iota H cross minus iota H cross LX. Alright, so what we get is we get iota H cross Y cap, iota square will be minus plus, so we get plus minus iota plus minus H cross square. So if you take the H cross common, okay, and if you take this, so what you are going to get from this, what we are getting here from here is it is H cross common iota Ly cap plus minus Lx cap. So this will give us plus minus. Okay, so this will give us, if you check it, this will give us plus minus H cross, okay, plus minus H cross L cap plus minus. Alright, so this is our commutation of LZ with L cap plus minus. Right. This is our commutation relation. So with L plus, it will give you H cross L plus, and with L minus, it will give you minus H cross L minus. Right, and our last two commutation relation, which are okay. So that is just so this is H and I are also similar. So H and I, last ones, they are also very easy, and we just have to add plus minus. So again, I will open and like we have proved already this thing. Sorry, this will be Lx cap plus minus iota Ly cap, right? Okay. So this will be L cap square comma Lx cap plus minus iota L cap square comma Ly cap, and we have proved that L cap square comes with Lx and L cap square comes with Ly. So both are 0, so we are going to get 0. Okay, so L cap square also commutes with this step up, this ladder operators or step up, step down operators. Alright, okay, and this complete our rerun of our previous section, and I hope you will be able to you'll be able to see these solutions on this video. Okay, thank you.